All right. So this is the motivation for studying refrigerant flammability. It turns out that a typical refrigeration system worldwide leaks about 10% of its total charge. That's incredible. So that means in your car, after 5 years, your car has leaked half of the charge. Now, cars don't leak as much as a lot of other systems. What leaks the most is large, big box stores like a Walmart, where you have a lot of field-made joints, and those may leak a lot more than 10% of the total charge. And all these leaks, they're harmful to the atmosphere. They're greenhouse gases. They're probably the second or third most important greenhouse gas after carbon dioxide, methane, perhaps ozone and NOx. So the first generation of refrigerants were CFCs and HCFCs. These had chlorine atom in them, and they damaged the ozone layer, which was then producing very harmful UV rays. And these were phased out by the Montreal Protocol in 1987. So now we've moved on to the newer products, which are HFCs, hydrofluorocarbons, and they've been used since then. They're not harming the ozone layer, but they have very high GWPs, typically on the order of 2,000 times those of CO2 per gram. So now we're looking also to phase those out. And the next generation is mildly flammable HFCs. So they break down in the atmosphere, which is good. They don't last as long up there, but that means if they leak into your house, they can burn. And so this is the burning hazard that we're going to look at. So these are classified by ASHRAE according to their flammability. And I should say that flammability is the main impediment to adopting these new molecules. So class 1, these are what you likely have in your car, in your house right now. They have no flame propagation. If they're heated enough, they can have a little bit of a flame, but according to the standards, they're not non-flammable. And now we're starting to adopt the class 2L, subclass 2L. These have a lower heating value that's low. I'll talk a little bit more about that, and a high flammability limit and a low flame speed. These are the three main determinants of whether a refrigerant can be classified as subclass 2L. And after that, increasing flammability, class 2 or class 3. Class 3 would be things like propane. It's a good refrigerant. It really works well. It works well in refrigerator systems, and butane as well in your household refrigerator, but it's much more flammable. So some examples of the 2L refrigerants that I'm going to emphasize in today's talk are shown here. R32, it's the canonical one. There's no patent on it. It's cheap as dirt. And as you go down the list, some of these get very expensive. The 1, 2, 3, 4, YF and ZE, produced by Honeywell and DuPont, now Nemours, they're very expensive. And they're a real moneymaker for those companies. So here's a drawing at the right of what R32 looks like. This is carbon, 2 hydrogens, and 2 fluorine atoms into a molecule called difluoromethane. It works great in refrigeration systems. It doesn't harm the atmosphere. It's not much of a global warmer, but the problem is that it's mildly flammable. So it's a lot less flammable than methane or propane. Most of us have methane in our houses. I have a propane stove, barbecue outside my house, which is much more hazardous from a flame standpoint than are these refrigerants. So the lower heating value, the heat of combustion, basically, the amount of heat liberated when it burns is low, about an order of magnitude lower than methane. Its laminar burning velocity also about an order of magnitude lower than methane. And its lower flammability limit is very high, maybe 3 times that of methane. So that's what you want. For flammability, you want something with a low heat of combustion, a low burning velocity, and a high lean flammability limit. So you need to leak a lot for it to burn, but when it burns, it's going to burn slowly and with a low energy release. Now, I should say this molecule is not hazardous really from a fire standpoint compared to something like natural gas that I have in my house, but it's toxic when it burns. And that's the topic on which I'll finish this seminar. Okay, there's some other important properties, and one thing I should point out that I like about this classification system is that all these properties can be measured in the laboratory for not much expense for a device that's very small and can fit on your tabletop. This is the auto ignition temperature, the minimum ignition energy, and that's a couple of orders of magnitude higher than for methane, and the quenching distance is very large for these molecules. So all these properties can be plotted up, as shown in this nice plot here made by Honeywell, by Seaton and Spatz. So these are 4 of the main flammability properties of refrigerants. Let me start with the first plot. This is heat of combustion versus burning velocity. So in the upper right, you can see methane, butane, propane. These have a high heat of combustion. When they burn, they liberate a lot of heat, and they have a high burning velocity. If these leak into your basement and become flammable when there's an ignition source, so they can actually explode your entire house into splinters. So the combination of high burning velocity, high heat of combustion is a high flame hazard. And you can see the refrigerants here at the lower left, R32, the 1234YFs, these have low heat of combustion, low burning velocity. So from a flame standpoint, they're much safer. And then the lower plot here shows the ignition energy versus the lower flammability limit. And you can see in the upper right now, the refrigerants, Y234 and the R32, these require a big spark to ignite them. And they require a lot of fuel, a rich mixture for them to ignite. Whereas look at acetylene or even methane, gasoline, all the hydrocarbons, doesn't take much of a spark to ignite them. And at very lean conditions, like 5% of volume, they can ignite. So on all four of these measures, the A2L refrigerants look a lot safer than natural gas. And they are from a flame standpoint. It's just from a toxicity standpoint, they're much more hazardous. So as our first experiment about 8 years ago to get into the flammability of A2L refrigerants, these mildly flammable refrigerants, what we took is just a tube and we flowed R32 into it, pure R32, and held a butane lighter up to it. And you can see on the left here is the butane flame, on the right is the R32 flame. And what surprised us is that when you withdrew the butane flame, the R32 flame went out. So at least for this burner size in air, this mixture, the R32 flame was not self-sustaining. And this kind of experiment can be a little bit misleading. It's led some true experts in the field to give the quote that igniting a mildly flammable refrigerant is like trying to strike a match in a hurricane. So if you're a cigarette smoker and there's a hurricane, you're not going to be able to light your cigarette. And even in the quiescent condition, it can be hard to ignite R32. But that is a little misleading. This experiment shows it's very hard to ignite, but I'll show plenty of other experiments with some videos where it does ignite. So this is the test that we did to show that. There are two chambers here, and the image on the left is a 27-liter box. It's an aluminum box with a window in the front into which we can leak the refrigerant, mix with air, and then ignite it with various ignition sources. And on the right is another apparatus that I'll talk about later, which measures the flammability limits, the lower flammability limit, which is so important for these refrigerants. So this is a video that hopefully you can see with the screen sharing, where a stoichiometric mixture of 4 different refrigerants is leaked into that 27-liter box and then ignited with a hot wire. So it's just a nichrome wire coiled up, energized with around 9 volts of direct current electricity. So when the electric current turns on, the wire glows yellow. You can see that in all these images, and it ignites the mixture. In all cases, the flame starts at the top and then burns its way down to the bottom. So these are blue flames, and the heat of combustion is low. They have to be very rich to burn, but they definitely ignite. And those flames are definitely hot enough to burn you if your skin were in there, or to ignite other materials, like if you had curtains or carpet or other furnishings. So this shows that when the mixtures are stoichiometric and you have a good viable ignition source, they will burn. They generally burn with blue flames. And in some cases, they don't burn all the way down to the bottom. They don't seem to burn the entire mixture. If you did this with methane or propane, you'd have a blast. You'd have loud noise. Everything would burn very fast in very energetic yellow flames, turbulent flames. So the next one I want to show is a safety match. So here what we did is we took a wooden match and we ignited the match inside the box to see how that burned. And it's similar to a hot wire. So a wooden match is a viable ignition source for these flames. And then this one I'll show, is the lighter flame. So if you fill the box up with a flammable mixture of the different refrigerants and insert a lighter, a butane lighter, this is what you see. So in this case, and for some of the mixtures, some of the tests, the butane lighter was a viable source. It got into the box and ignited the mixtures. But for some other cases, it actually was suppressed. The flame did not propagate all the way through. And these are definitely flammable mixtures, but it does show that the mixtures can be difficult to ignite. The easiest way to ignite them is a hot wire that stays in there for a few seconds. When you take a relatively weak flame like this butane flame and try to pass it into the box, often it will not ignite. All right, and then the last one I want to show, which is also, maybe more surprising, is a leak on a candle. So in these 4 tests with the same 4 refrigerants, we ignited a candle, just a taper candle from a dinner table, and then we leaked in the refrigerant into air. So initially the candles are burning strongly, the refrigerant comes in, it's cool and high molecular weight, so it generally cools below the candle and then fills the box from the bottom. Even though the leak was above, it cools and fills the box. And what we find in all these cases is that the refrigerant actually puts out the flame. So the flame doesn't ignite the refrigerant. You don't get this full flame enveloping the entire enclosure. At least in these tests, 27 liters, the refrigerant acts like a suppressant. It actually puts out the flame. And that was a surprise. So what it suggests is that if you're in a hotel and you're burning a candle and the PTAC system leaks into your room, it's likely to put out the candle instead of igniting the refrigerant and having a big fire. All right, now the last one I want to show is the effects of concentration and turbulence. So far, most of the tests were at low concentrations and without much turbulence. But these are slowed down videos, and you can see they're very energetic. So on the left, we have a hot wire ignition of R32 stoichiometric. I'm sorry, a little bit lean. And on the right, we have a test that's much more energetic. It's a richer mixture, very close to the stoichiometric condition, and the mixing fan is turned on. And that turbulence, instead of having a mostly laminar flame, that turbulence makes the flame propagate much faster and completely fill the enclosure. So whenever you're talking about explosions and blasts, there are a few things that make them more dangerous, and you can see that here. Having a very rich flame tends to make it more dangerous. Having more turbulence makes it dangerous. Confinement causes pressure to increase. You can get a blast wave. And then congestion, if you have a lot of obstructions like bushes or furnishings or pipes that you might have in an offshore oil rig. So, on the one hand, you can see that these flames can be very mild, very weak, and put themselves out. In the other case, under the right conditions, they have been seen, and we even see this here, to generate a blast that makes a loud sound and that can break objects. But nowhere near the flammability and the blast hazards that you would get with propane or methane, natural gas that we use in our homes. So this is a summary. We tried a lot of other conditions that I didn't show here at the bottom. Maybe we should start with that. When you put a cigarette into this box pre-mixed, it doesn't ignite the mixture. Let's see, when you try to strike the barbecue lighter inside the box, the spark cannot get the barbecue lighter to burn or the contents of the box. We did plugging in plug in a receptacle under high amps, I think 15 amps with big blue sparks shooting out, and that wouldn't ignite it. Light switch, same way. Electric hand mixer, electric cordless drill, even friction sparks. All these things get Ns under the 4 refrigerants, indicating that they could not ignite the mixture. A hot hair dryer at maximum power did not ignite it. Even a toaster, a bread toaster, even a hot plate, a boiler plate, and a space heater insertion. I think almost all of these ignition sources would ignite methane or propane. We didn't test it because it's rather dangerous to do those tests, but they won't ignite any of these refrigerants. What is viable to igniting them is a hot wire that's exposed. Well, we don't have those things in our houses. A safety match, if it's already burning. A lighter flame, if you walk into a hotel room that's had a leak of refrigerant with a lighter flame or a candle, you're probably going to ignite the entire mixture. And the leak impinging on the candle was kind of hit or miss. In some cases, it did ignite more of the mixture. So having learned this about the ignition, I want to show another experiment that we performed where we looked at the flammability limits. As you'll recall, the flammability limit is an important characteristic of these molecules. And I'm sorry, I got a little ahead of myself there. Let me point out that there's a bunch of molecules shown here that consist of carbon, hydrogen, fluorine, and in one case, oxygen. And so you can see that depending on the number of atoms of carbon, hydrogen, and fluorine, you get different molecules. and that some of these molecules are refrigerants and they're mildly flammable. So the R32, 143, and 1234 at the top, these are refrigerants, they're mildly flammable. But if you change the composition just slightly, you get molecules that many fire protection engineers are familiar with. FM200, Novec 1230. These things are suppressants. These are used when there's a fire and you need a clean agent in a server room. Then you flood the server room with FM200 and Novec 1230 and it puts out the fire. So that's, I think, why we see some apparently anomalous behavior when you have leak impinging on a candle. The refrigerant sometimes acts like a fuel and sometimes acts like a suppressant. And we've seen that also in work with Greg Linteris, that sometimes the suppressant can actually act like a fuel. In the FAA canister tests, you can see that some of these suppressants actually enhance the fire behavior. So fluorine in general at the bottom here suppresses fires, whereas carbon and hydrogen are the fuels. So it's really the ratio of the fluorine to the carbon number in the molecule that determines whether it's a fuel or a suppressant. So the takeaway here is refrigerants can suppress fires. We saw that with the candle. And suppressants can enhance fires. And that's been seen by other researchers. Okay, now I want to switch gears and talk about the lower flammability limit. This is a really important characteristic of refrigerant molecules. Now, a lot of the manufacturers are looking at mixtures. And so they want to tailor the mixtures so that they get good behavior in their HVAC system, but also so that their LFL can fall into the class 2L category. That allows you to have a much higher charge in your air conditioning system. So these are measured with ASHRAE 34. It's the ASTM E681 flammability limit. And it's a really nice apparatus because almost any laboratory can build one for about $1,000, and it doesn't require any special skill or special equipment. So, and that's one thing I like about it. It's an inexpensive standard. It's all in use all around the world. And another thing that I really like is that you see the flame. It's in a glass flask, a 12-liter glass flask, and you see the flame. You see it with your eyes. And it's not just looking at some pressure trace or some other measurement. You really see the flame. That, as an experimentalist, that's very appealing to me. So this is the standard for determining lower flammability limits, not only for refrigerants, but also for hydrocarbons. Now, for refrigerants, there are several major problems with the existing standard, and those are summarized here at the bottom. One is glass etching. After 5 to 10 test runs, because you're making HF, hydrofluoric acid, it etches the glass, and it eventually becomes like the windows in some public bathrooms, totally white, you can't see through. So that's very costly at $250 a pop for the new flask. They can vent during the test, and it depends how people set this up. It's almost like having a thumb on the scale. If your boss says, hey, this is a mixture I want to sell, we want to make sure that it's not flammable, well, they just adjust how it vents and they can change the behavior. And then the vertical electrodes can be a problem. So let me look at that a little bit more. Here's an image of two tests that show one test at 2 different times where it shows the rubber stopper venting. And so it's a little hard for you to see this, but above the box there, you can see the rubber stopper and it's shooting up several centimeters. And if you're venting into the neck of the flask and at the same time trying to observe the angle of the flame, looking for a 90-degree cone angle, that's very subjective and really varies from lab to lab. So we did some work to try to improve that, and I believe we did. First, let me talk about the polycarbonate flasks. So figure A is a brand new glass flask, a $250 flask, 12 liters, beautiful and clear. The first test, you see the flame beautifully. And figure B is a glass vessel that's been etched by about 10 tests. And so you can still kind of see through. If you're trying to save your boss money, maybe you say, oh, okay, I can get 3 more tests out of this. And suddenly you're trying to measure a flame angle while you're looking through with, very bad sunglasses, very dirty glasses. You just can't see through it. So in image C now, one of our students, a real rainmaker, was able to find a replacement that's made out of plastic. It's polycarbonate. And we looked and looked and looked and had no luck. And boy, he found it right away. And this is a lighting dome, like you might see on a street lamp in a public park. And so this lighting dome now has a 12-liter volume and it's plastic. And we burned this thing 50 times, 70 times, and never had any etching. And it's also nice because you can drill it and change the penetrations. So this is a schematic of the new apparatus. Instead of having the electrodes and the thermocouple come down from the top, as you need to with the glass, it's just so easy to drill in it with a drill and provide the electrodes and the thermocouple from the bottom. And there's that 90-degree angle that defines whether a flame, just by convention, if a flame burns outside of the 90-degree angle, it's considered to be flammable. If it burns less than 90 degrees, it's considered not to be flammable. And I guess the rationale is if a flame ignites in your home and it burns upward at a 90-degree angle, it may not ignite anything else. It may burn to the ceiling and then burn itself out. But just by convention and historically, this is the angle that's chosen. So I'll show a couple of videos here. When we were able to change the orientation of the electrodes, it changed the behavior a lot. So on the left is the standard with the electrodes going up, but they're right in the strongest part of the flame. They weaken the flame and they slow down the flame propagation. When we move the electrodes out of the flame path, we get a much cleaner flame that burns faster, so it does slightly change the flammability limits, but it's a much better, more reproducible standard. So this is two images of one on the left with the vertical electrodes and the horizontal electrodes. Me, I just much prefer the flame burning in an open environment on the right with the horizontal electrodes. So here's some still images of some flames, but I think the video that you saw shows this a little better. So in the standard, what they require is that you do at least 2 tests. And if 2 out of 3 times it's above or below 90 degrees, that defines for that molecule whether it's flammable. And we realized that statistics aren't very good. So instead what we did is we fit a plot of flame angle versus concentration as shown here, and then find where that intersects 90 degrees. It gives you much better statistics. Instead of just basing your test on your flammability limit on potentially 1 test or 3 tests, now you can base it on 10 or 12 at various different mole fractions. So this, I think, gives much better statistics for the method. So this then summarizes the changes that we recommend to the standard. It takes many years to get these changes in. We've published this in a peer-reviewed journal paper, and we're continuing to visit the standards writers to try to get this changed. But we want to change the material from glass to polycarbonate. We want the electrodes and temperature probe to be horizontal instead of vertical. And we want a statement in there that venting should not occur during flame propagation. How are you going to measure an angle of a flame where it's being sucked up into the neck of the flask as it's propagating? We were able to avoid that by putting fixed weights on top of the stopper. And then the flame angle should be plotted versus mole fraction instead of just doing 2 out of 3 tests with lower statistical bounds. Okay, and now the last topic I want to talk about is the HF hazard. So anytime you heat fluorine, it wants to form HF. That's thermodynamically most stable molecule for endpoint for fluorine. So if you burn Teflon in your kitchen on your frying pan, you're going to make HF. If you burn refrigerant in your house and it's mildly flammable, I know some people say it's like igniting a match in a hurricane, but if you're able to ignite that match in that hurricane, you're going to make HF. Basically 100% of the fluorine atom is going to become HF. The closest most of us have ever come to HF is like this bottle at the right that dentists use. So they can buy this stuff and it etches ceramic. It's such a good acid, it etches ceramic before they put the crown in your mouth. So dentists work with this. They have very careful procedures to protect themselves and their patients. So what I want to say is that HF is a greater hazard than the other 3 flame hazards combined. And the 3 main flame hazards in your house would be secondary ignition materials, thermal injuries, and blasts. So if you talk to firefighters, and I've talked to firefighters about this and large groups of firefighters, in fact, and they're like, don't worry, if that burns in your house, we got it under control. It's going to be a small flame. It's going to go out fast. We're going to prevent secondary ignition materials or stop that. We're going to save you from the thermal injuries and protect you after the blast if there ever could even be a blast. But what the firefighters are worried about, what I'm worried about, is the HF. So when you leak, a couple kilograms of this refrigerant into your house and you burn it and you're making kilograms of hydrofluoric acid in your house, that's a real problem. It's a real problem for people inhaling it and on all the surfaces. So why is it a problem? Well, first of all, you produce a lot of it. Here's the stoichiometry. Thermodynamically, all the fluorine in these molecules, when they burn with air, wants to become HF. And so depending on the molecule you have, either, you get different concentrations of HF in the reactants, but you produce a lot. Methane, of course, has a lot more energy of combustion, but doesn't have any fluorine in it. So another molecule you'll see here for the dry combustion of the 1, 2, 3, 4 refrigerants is COF2, and it's even more toxic than HF. So the bullets here are that you can produce, it's been quoted up to 15% HF volume fractions if you have a refrigerant fire. So, given volume, a hotel room, after a fire, you can have up to 50% of the volume fraction is HF. And it can be produced on heating even with no flame present. We see that in our kitchens. People complain about their canary dying. It was in the kitchen because people were doing a lot of cooking with Teflon stoves, and it's attributed to HF. So first responders, fire investigators, and construction personnel will require specialized training and medical supplies if they're responding to refrigerant fires. Okay, so HF is one molecule. The other one is COF2, carbonyl difluoride. These carbonyl difluoride is more toxic than phosgene, which is a well-known chemical agent banned for chemical warfare. So both of these molecules are as bad as anything used in chemical warfare. So NIOSH establishes limits for these, 2 parts per million for a 10-hour workday. Luckily, you can smell this stuff. I've smelled it a couple times at about 1 part per million. So your nose is a good detector, but if it's at 50%, are you going to be able to get out before you breathe it or before it attacks your skin or collects on surfaces? I'm not so sure. And then the lethal dose here is 50 parts per million for 30 minutes. So certainly 1 lungful at 50% concentration is going to do a lot of damage. So HF, it causes damage in lots of different ways. It penetrates your tissues easily. And the problem is then it gets into your blood and it binds with calcium and magnesium ion. And this is what causes cardiac arrest. So symptoms can be slow to appear. Some people report they get HF on their hand and it doesn't hurt. It doesn't hurt at all. And so they don't get treatment fast enough. So that hypocalcemia, the HF gets into your blood, it actually precipitates the calcium in your blood and makes tiny bones. It's very painful. But also when you lose the calcium and magnesium in your blood, that your heart needs that to operate properly, and you go into cardiac arrhythmia, and that's the most likely fatal consequence, cause of fatality. So it's reported that death can result from exposure of just 2.5% of your body surface. So that's the size of your hand or your foot. That's enough. Your hand splashed on HF, your foot splashed on HF. If you don't get treatment, can be fatal. And then the burns are horrible. I don't want to show any pictures of these, but if you get it under your fingernails, it can last there for weeks and kill the tissue until often your finger needs to be amputated. So this HF is really nasty stuff. It's not only used by dentists, but it's used for etching silicon. The worst incident I've read about was a trash collector in New York City. For someone, and maybe it was a dentist, had thrown a bottle of this in the trash, and when it was in the compactor, it sprayed on the person. They didn't know what it was. There was a fire station right next door. They got the quick treatment, but no one knew how to treat it, and the trash handler perished. Okay, so I don't want to go over all this, but there is good first aid. For us working in the lab, we're able to provide these treatments for HF, but the typical person in their home or hotel room won't have access to this. So I don't want to discuss this slide, but there is good treatment for HF. Okay, so there are 2 incidents that I want to talk about at a very famous laboratory all of us have heard of, a famous fire testing lab. And they had 2 injuries with HF while they were doing A12 burn tests. And as shown in the last bullet, after that, they decided, okay, forget it. No longer we're going to burn with halogens. So this was recounted in public at the Purdue Refrigeration Conferences a couple of years ago, but the company has not released any official statements on this, so I don't want to identify them by name. So they had a burn room, kind of like what we were doing in the 1-foot cube box, but in a big room, and they burned some halogen refrigerants, and an employee came in the room after without the required protective equipment. Now, he was trained, he kind of knew what was going on, but something caught on fire. I think it was a plastic part of an HVAC system, and he came in with a fire extinguisher and put it out, which is what you would do, right? If you had a methane fire, you'd come in, put it out, and be no problem. But the HF condensed on his skin and on his skin surfaces. He went home feeling a little bit itchy and scratchy. He didn't feel so good. He took a shower, and he collapsed. So he went into cardiac arrest. Luckily, his wife was home, and he got to the hospital and survived. So this is a well-trained technician at one of the top fire labs in the world. And then another time, after a different burn test, and lots of air changes, another employee came into the burn room, and you know how you tend to just lean your hand on the wall, and suddenly felt pain. And so even after flushing with air, there was still HF on the wall surfaces. They hadn't used any water, so but it was condensed on the wall, and it was enough to burn the person. So this laboratory no longer allows these burn tests. We have been very careful at UMD, and but still, every time I ignite one of these, I'm nervous. Okay, so what could happen in real life? Well, imagine you're in a hotel room and your PTAC system leaks. That's kind of the wall shaker or the window shaker in your hotel room, and ignites by a candle. You get a small fireball, but it doesn't burn anything else in the room. And so the guests, it smells bad, but they don't really know what it is. They stay in there. Maybe it happens when nobody's in there until someone comes in, and now they're exposed to inhaling HF without understanding what this is and how toxic it is. The second scenario, imagine your supermarket reach-in cooler that uses refrigerant, and somehow it ignites. There are lots of ignition sources. In many states, you can smoke inside these stores, but it could even be the lamp or the switch on the wall. You know, the fuel tends to find ignition sources when you have enough fuel leaks. And imagine you get this blue flame and it goes out, but now you have HF on all the packaged food. So customers who are getting it on their hands may be ingesting it, and the employees as well. And the third one, imagine that there's a small fire after a refrigerant leak, and firefighters respond. They suppress the fire using all their normal techniques, and then like, okay, this is good to go. They remove their SCBA gear, and now they're inhaling HF during the cleanup. If they're not trained, they don't know what this is, they'll have inhalation issues. You get that same kind of tissue necrosis in your lungs when you breathe this stuff. So firefighters are going to need to be trained. The turnout gear is going to need to be cleaned in special ways. So this is kind of a sad note to end on. You know, this was meant to be a talk about, and all this has been work for me about refrigerant flammability. What are the flammability characteristics? That's the stuff I'm really interested in. But it turns out the real hazard with these molecules, with these refrigerants, is the chemistry. It's not the flames. The flames are mild. Those are fine. I think we can handle the flame hazard. The real hazard is the HF that's produced. So I think eventually, in my opinion, something's going to need, some new molecules are going to be needed. Maybe it's carbon dioxide, which unfortunately requires super high pressures. Maybe it's ammonia. Heck, I'd rather have an ammonia leak in my house than have one of these fires in my house. You can smell it and you know you want to get out quickly, and it's not as bad. And there are other molecules that people are looking at that aren't halogens, that don't have this fluorine atom. You know, fluorine is the root of the PFAS, the forever chemicals that people keep talking about in the environment. So let me end this talk then by talking about some large scale tests that we did on campus. So at the left, there are two images of a PTAC that we forced to intentionally leak and a halogen, R32, and ignite it with candles. And you can see a small flame that ignites and burns and kind of goes out. It could maybe ignite something if this were a hotel room. Maybe it would ignite the carpet or the bed if it were close enough, but maybe not. It's not that scary of a flame. But what's scary here is the HF that you smell afterwards if you go into this enclosure. The image at the top right there is a bonfire test under a similar PTAC unit. And this, what happens with this is the flames heat up the refrigerant to very high pressures, and they weaken the containment, so that when the containment fails, it's like a rifle shot. It's very loud, and you get a very energetic jet shown at the upper left of that image, a yellow jet of fire burning. And then perhaps the most dramatic test we did is the one on the bottom there. This is an 8-foot high enclosure meant to mimic air handling room in your basement. So imagine you have an air handler in your basement. It's cooling your house or heating your house, and that leaks. That leak finds maybe a pilot light on a hot water tank or something and ignites. This is a scenario that's looked at here. In this case, it was very energetic. It's a lot of fuel and very energetic. It blew the curtain. You can see the curtain being blown forward, and it lifted the roof. This is a 1/2-inch plywood sheet, and it lifted that up by a couple of inches. So it actually did make a blast, a very energetic explosion. So these are some large-scale dramatic tests that are fun to look at. To me, with my expertise and my background, I like working at the bench scale, safer, more confined tests. But I hope this gives you a brief introduction into the issues remaining today with refrigerant flammability. And with that, we'll open up the floor to any questions you may have. And Sebastian, if you can help me manage the question answer session, that would be good. One person's raised their hand, I can see.
Yes, yes, thank you. Thank you for that, Dr. Sunderland. Yeah, so let's get to the Q&As right now. We do have one person who raised their hand during the presentation, so I'll let them go first. Yes, so the person who just raised their hand, you are now, you should, if you're able to unmute, you can now ask your question. Okay, that does not seem to be, the unmute function doesn't seem to be working. If you wouldn't mind, I do apologize, chatting your question. Dr. Sunderland, we do have one question in the Q&A chat box from Nicholas, if you would be able to respond to that.
Okay, can you read it back to me?
Yes, the question is regulating charge size the best or most effective way to mitigate the hazard of A2LS? Is this why air changes per hour are important, perhaps to lower flammability limit and prevent ignition or dilute subsequent HF? And the third part is there any training available to first responders and HVAC technicians on this topic?
Okay. Okay, so the first one, yes, I think regulating the charge size is a smart way to go. So if you're in a hotel room, and this is exactly what's done, depending on the volume of the room, that defines the number of grams of charge you're allowed. So the scenario is that all that charge leaks into the room, it mixes up, you want it to be below the LFL so it can't ignite. So charge limits are an excellent way to protect against having a flame. And if you protect against the flame, then you also protect against HF, which is really the biggest hazard. So I do agree with regulating charge sizes. It's a little tricky because what if the hotel owner then makes those rooms smaller for some reason, takes a double room and makes it into 2 separate rooms. So it's a little hard to manage, but regulating the charge side is really a wise thing to do. And that's the way that all the standards are going. That's why in refrigerators, like in your household refrigerator now, they're going to propane because those charge sizes can accommodate propane in a refrigerator. Okay, so air changes are really tricky. So, most systems, okay, the HVAC systems, most of them are going to have sensors in them that can detect a leak. And when they detect a leak, the instruction is going to be, okay, turn on all the fans, blow every fan in that system. And all these systems have multiple fans, turn everything on and blow it all around. And the idea is then as soon as you detect it, you want to dilute it down, mix it up and get it out of the residence. So I think having air changes is a wise thing to do, but we've also seen that turbulence makes the flames more energetic and burn faster. So some people say it can be worse. If you have the refrigerant pooling in your duct and you turn on the blower, maybe that's going to provide the ignition source. All blowers are potential ignition sources and you'll actually ignite it. So having more flow generally is thought to be a good thing, but it really depends on the scenario. Okay, and then so training for technicians and firefighters. Technicians are going to need new training. Right now, they sweat these fittings with a torch. So if you have a leak in my house, right?
Sorry
yes,
about that.
we can hear you. So they use a torch a lot of time to make the fittings, and you don't want to use a torch if you have a mildly flammable refrigerant. So technicians are going to need new training. A lot of people who service air conditioning systems, they're working in the back of their pickup truck. And they got a bunch of bottles of the different refrigerants in the back. Maybe sometime they don't have the one they want. They're going to put a flammable refrigerant into a system that doesn't say flammable refrigerant. It's going to run fine. The people aren't going to notice anything in their residence. So there are thousands, maybe millions of refrigeration technicians, people who work on refrigeration systems just in the United States. The number of people that need to be trained is tremendous. And as far as firefighters, yes, this is something also, it's really a big concern. It's really right now going department by department, jurisdiction by jurisdiction, but I can try to put you in touch with people if you want to send me an email with people who can help you with that kind of training. But thank you for those good questions, Nicholas.
Thank you, Dr. Sunderland. Okay, so to our participant, you raised your hand. You should be able to speak now. Would you like to ask your question? It doesn't seem to be working. Okay. So, okay, we do have some questions that came in. Yes, this person asked 2 questions in the Q&A section. The first one was why was the R32 refrigerant used in the FCU?
Oh, FCU. What, I don't know what FCU is. I'm sorry.
I do apologize. It was sent. Okay, we'll get back to that one. The other question was, can non-flammable refrigerants ignite?
Okay, great question. So you saw in that 12-liter sphere that the 90-degree cone angle is defined as flammable. If it burns outside of that, it's flammable. Inside of that, it's not. So yes, even the non-flammable, the A1 refrigerants can ignite. And especially if they're heated, they can ignite. So if it's leaked into a hot room, a hot area of a hot attic, then increasing temperature of the air in the refrigerant makes it more flammable. So yes, they can ignite. And you got to draw the line in the sand somewhere and say, okay, it's 90 degree, that's where we're cutting it off. These ones are quote unquote not flammable. These are burn outside 90 degrees and they're quote unquote mildly flammable. So that's an arbitrary line, and definitely even the ones that are stated as non-flammable can ignite, but it's harder and it's rare. They won't really sustain their own flames. Very good question.
Thank you. Okay, the next question, to go back to the one that was asked with the FCU, the participant said the FCU means fan coil unit. So why was the R32 refrigerant used in the fan coil unit?
Okay, well, one reason we like R32 is because it's dirt cheap. And 1, 2, 3, 4 YF and ZE, these are very expensive. And so as the canonical molecule to use for these, R32 is what people generally use. So in Japan, they love R32. They have millions of systems and units in service, and they haven't had any accidents. Now, these are all new, right? They're new and not leaking, but so far they haven't had any fires. So really, if you're going to pick one molecule to represent the class of mildly flammable refrigerants, R32 is the one to pick. There's no patent. It's very cheap. Anybody can have it and buy it. And its flame properties are the best understood. But we think that the behavior wouldn't be too different. If you ask Honeywell or Nemours, they have reasons for arguing that the 1, 2, 3, 4 YF and ZE are less flammable. And on some measures they are. But we saw in our ignition tests that it wasn't night and day. These all kind of behave similarly. But thank you for asking that question.
Okay. Another question that's come in, do we have leak detectors to monitor leaks in refrigerant systems?
Excellent question. So this is something that we're working on now. And the leak detectors, they exist, but they're expensive. They're, you know, a nice optical leak detector is $500. But the manufacturers who are selling millions of air conditioning units, they're going to be required to have a detector, and they want them to be $10, and they want them to last 10 years. So currently the technology doesn't exist. The two main sensors types are MOS, metal oxide semiconductor, and also NDIR, infrared detectors. Those are the two technologies that exist. Of course, when you scale up, it's going to be like smoke detectors. They were super expensive when they first came out, and now you can buy one for $5. So we think the sensor price will come down, but it's still an issue with lifetime. And you don't want, just because your sensor goes out, you don't want to have a technician come every time and replace it or troubleshoot your system. So right now, the #1 impediment to adopting these refrigerants is a flammability hazard. And the #1 impediment to protecting against that is the lack of the sensors. So really, that's really what we need, is better sensors. Excellent question. Thank you.
Wonderful. The next question that's come in is from an anonymous attendee who asks, how would you dispose of flammable refrigerant safely?
Well, let's see. Good question. So I think it's the same as you dispose of freon. So these CFCs that contain chlorine in old systems, plenty of houses that still have these. I have a beer cooler in my basement, wine cooler, that still has freon in it. It's the chlorine. So you can't just put that in a trash compactor and let that leak. You're required to recapture that. So technicians have the pumps, and they bring it to a transfer station in their community. So that needs to be collected. Now, if it's methane or propane as the refrigerant in a modern refrigerator, you can just bleed that off. But the older refrigerants, especially with these high global warming potentials, those need to be recaptured. So and for your resident, I guess you'd go to your county or your town. If you're doing it at the campus or in a company, they need to recover just like any other toxic material, the waste materials. Good question.
Mhm. The next question is, why do refrigerants act as suppressants to candle flames? Are there any other instances where refrigerants act as suppressants?
Okay, so we found that we put a cigarette in our box and it would burn for 10 minutes until it went out. And then we took the same cigarette burning and put it in the box with the refrigerant and it put out the cigarette. So incense won't burn when you have the refrigerant. It acts like a suppressant. The cigarette won't. Depending on how fast you raise the concentration, even a candle will go out. So there were several instances where the refrigerant act as a suppressant, as a fire suppressant. I wouldn't recommend it for a clean room to protect your clean room as a fire suppressant, but you know, if you want to protect against people smoking, certainly it would work. So yes, it's very surprising. The flammability of these molecules is not straightforward as it would be with methane. Methane is always going to add to the energy release if you have an ignition source, but it can be a surprise when you involve the fluorine atom. Thank you.
Okay, the next question that's come in is, how much is known about why refrigerants leak from their systems? And how can that 10% per year rate be reduced by the consumer?
Okay, well, you know, my wife works in the processed gas industry, and what she'll tell you is that every pressurized gas containment system leaks. You cannot stop leaks. Even if you just have a K bottle, you know, thick aluminum bottle in your lab with a really beefy valve on it, 2000 PSI, you know, in 10 years, it's going to leak out 100 PSI on a brand new bottle. So that's very simple. Something with hundreds of fittings in it, like an air conditioning system, will leak. Even the joints made in a factory, in a well-conditioned factory for the heat exchanger, which have tons of passages and lots of brazed joints, even a certain number of those joints leak. But really the worst ones are the field-made joints. So someone on top of the building at Walmart connecting these fittings together, trying to break, there are lots of different ways to make the fittings, but they all tend to leak. The pressures for these molecules is somewhere around 250 PSI in operation. And so you have a good driving force that all it takes is a small scratch that can cause this leak. And I think people are being trained better on the leaks, but it's, you know, there's a lot of vibration. That's the reason they call these things window shakers. They sit there and vibrate. And so even out of the factory, a window shaker doesn't have any leaks. Eventually that vibration is going to cause the fittings to move and to start to leak. So I think that we'll never be able to reduce that 10% number down, but we'll never be able to eliminate it. What we really need to do is to try to find molecules that when they do inevitably leak, they cause less of environmental damage.
Okay, great. We do have a hand raised, so let's this participant allow them to talk. Let's see. Okay, could you please unmute yourself so that way Dr. Sunderland can hear your question? Okay, there seems to be some technical difficulties. So we'll continue on then with the question here in the Q&A queue. There is another one coming in. So are there any UL listings for refrigerants?
Yes, thanks for your question. The standards, the codes and standards are from many different organizations around the world. They're not perfectly harmonized, but certainly UL has lots of standards. They certify any type of, that I can imagine, any type of home cooling system or air conditioning system for your car. So they certify these and they do have standards, and they are now looking at the charge limits and the type of sensors that need to be adopted. Yes, UL is an excellent source for standards on refrigerants.
Okay.
And every year they're coming out with revised standards.
All right, wonderful. The next question is, what is the difference between a refrigerant and suppressant based on a clean agent?
Okay, let me move back to that slide. So, you know, the top table here is the refrigerants and the bottom table is the suppressants. And all these have carbon, hydrogen, and fluorine. And the big difference is that suppressants have a lot more fluorine than carbon, 5 to 2, 7 to 3, whereas the refrigerants have roughly equal numbers, 3 to 2, 4 to 3. And so the carbon and the hydrogens, those act as fuels, and the fluorine acts as suppressants. So when you have a lot of carbon, a lot of hydrogen, like these refrigerants, compared to the amount of fluorine, it's more likely to act like a fuel. And when you have a lot of fluorine compared to the carbon and the hydrogen, it's more likely to act like a suppressant. But there's no clear line in the sand that, you know, a 1-to-1 ratio or 2-to-1 ratio defines it. The refrigerants can cross over and behave like suppressants. The suppressants are known to cross over and behave like fuels in some cases.
Okay, wonderful. Yes, the next question that's come in is, how do you tell if a refrigerant will act as a suppressor or be flammable?
I think the best way is to put it in that 12-liter sphere like we showed, the E681 sphere, and do a flammability limit test. And dozens of these tests are needed because there are dozens of mixtures, dozens of individual refrigerants, and then an infinite number of mixtures of these refrigerants. So lots of companies are tweaking them. They'll try 40, 60, then they'll try 50, 50, 70, 30, changing the mixture and looking at the properties. There's no clear way, there's no formula that you can plug it into and see if it's flammable. People are working at that, they're trying to get that, but really the test is inexpensive and dozens of labs worldwide can perform that test. So the best way really is to perform the experiment in the sphere. Now the sphere needs to be improved. There's some problems with the test as I've mentioned, but it is the best way to determine it. Thank you.
All right, the next question is, how serious is the issue of HF burns from frozen food packages and hand-in freezers?
It's hard to know. There's no reports so far of this happening. So you know, I'm very clear in my laboratory what the hazard is. With my students igniting this stuff, I'm very clear and very concerned, and safety is job one for us. It's hard thinking in your house how it can be as much of a hazard, but I think I outlined that in one of my later slides that that these things can happen. So you know, there have been injuries like this. If you Google it online, where refrigerants have leaked from houses, and then there was an ignition source. But usually it was a case where someone was welding or putting the wrong refrigerant in the wrong system, not with a new system. These refrigerants are new, the systems are new, and they haven't had a lot of leaks yet. So my scenario is just me thinking, what's the worst thing that can happen in your fast food store? A leak in a reach-in cooler that gets ignited. Maybe that's completely far-fetched because it's hard to ignite this stuff. Hopefully you don't have a leak. Most of those leaks are actually happening on the roof. And so maybe it's far-fetched and it's not likely to happen. But we do know when HF is formed, it likes to condense on cool surfaces, cool, moist surfaces, and it can stay there for a long time. But thanks for that question too.
All right, wonderful. So do we have any other questions from the audience? No, that seems to be all the questions we have. I think will be today is a good stopping point. So I want to thank you all again for tuning in to our first of many faculty lecture series we have. Thank you again, Dr. Sunderland, for your time and that very informative presentation on refrigerant flammability. If you all do have any questions, either for our department or for Dr. Sunderland, feel free to visit our website. You'll see all of our contact information up there. Dr. Sunderland and the rest of our department will be very happy to answer any questions that you all may have on this topic or any other of our faculty's research topics that they're currently doing.